Start recording. Okay. So while you guys are getting stuff out, I will just talk about general logistics. Actually, didn't really prepare to speak too much today, so this will be interesting. But okay. What is what do we have? So, right, so there's a few new people. Hopefully, you will meet them. You will learn each other's names. All of you are on the Discord, I hope. So that shouldn't be a problem. Now, the topic of this year's reading group, this will be a year-long thing, not a half a semester, not a semester-long thing, because I feel like this will require a little bit more time than just learning some basic facts about quantum mechanics. So what's the topic? What did I say the topic was? The topic was mathematical introduction to topological insulators, right? So those are some words. Intro. Please don't write this down. This is like meaningless for now. To topological insulators. Now, this perhaps this isn't exactly what we're going to do. The idea is that, what I want to do is I want to study the mathematics of fiber bundles and then apply that to topological insulators. Okay? So the kind of idea is study, actually maybe not fiber bundles, probably we'll only really discuss vector bundles, but okay. Fiber bundles, and apply to physics. Now, the part where we're going to apply this to physics, we'll specifically try and apply to this idea of topological insulators. So this is roughly what I would love us to do over the next kind of year. Right? We learn about what fiber bundles are, we then apply to topological insulators. Now the point is, why I'm not saying this is quite just a study of topological insulators. This idea of studying the geometry of fiber bundles applies in physics like in many, many places, not just topological insulators. So, okay, I'll kind of briefly maybe talk for a second about, what is a fiber bundle and why might this be useful, but I won't go into any rigor or detail. So a fiber bundle, the idea is you have some initial kind of space, some manifold that you start with. And then on this manifold, you can glue another space to it at every single point. Right? So for example, like a great example of a vector bundle is the tangent bundle of some manifold. So for example, suppose I have a sphere. Do you agree? Okay, this is some manifold, whatever that word means, right? This is an object which is a two-dimensional flat surface. What does it mean, two-dimensional flat surface? It means that I can give it local coordinates, right? I can kind of separate it into little patches, and then I can look at the little patch here, look at the little patch here, and then talk about kind of this patch as like a little piece of R2. Do you agree? So I can kind of, I can think of a sphere as a bunch of bits of like little blobs of R2 that are kind of mounted to the sphere, and then I can construct the sphere out of these patches. Okay. But now what I'm going to do is I'm going to take and that at every point on my sphere, if I'm standing on a sphere, there's certain directions that I can be going, right? On the sphere. They're kind of this way, but I cannot be going kind of away from the sphere, right? If I have to stay on the sphere. So what I can do is I can attach at every point a plane, which is tangent to my sphere. Do you agree? So think of this object, which is my sphere, and at every point I attach a plane, right? So I kind of get this interesting set of kind of points on the sphere with planes attached to them. Do you agree? Okay. And that is an example of a vector bundle. Do you agree? So it's like the sphere with tangent planes attached at every point. Okay.
Is it the plane that's a bundle, or is it the point and the bundle?
So it is the total set of my sphere with planes glued at every point. So an element of the set is some vector at a point. Do you agree? So that would be the idea. So tangent bundle, I glue so glue tangent plane at every point, right? So meaning the points of a tangent bundle, a point in my tangent bundle is a vector at point P. Okay? So, for example, my tangent bundle would have, say, this will be an element of my tangent bundle as a set. Okay. And there is certain interesting, topology and whatnot that I can do. Okay. Now, so what happens in physics? Like, one interesting question that we can ask, well, not interesting question, like one phenomenon that is of interest to us is this concept of parallel transport on vector bundles. This is what appears in physics, it seems like everywhere. On vector bundles. And I'll just give you a quick example using this sphere analogy. Okay? So let me move this away. Move this back. This is all kind of a loose hand wavy exposition. You're not meant to understand or remember any of this. Okay, so I have my sphere. Do you agree? Okay. And now suppose I have at the top of my sphere, I have some direction vector that is pointing, let's say, this way into the board. Okay, going this way. Okay. Now I can look at a path that goes kind of down like this to the equator. Do you agree? And I can parallel transport this vector along this path this way. Do you agree? And so if you follow my hand, I parallel transport it down the plane. It's pointing still kind of this way. Do you agree? Okay, so it's still pointing this way. Do you agree? Now I can translate it along the equator, somewhere here. Okay. And this, if I parallel transport it this way, the vector is now pointing this way. Do you agree? Okay. And now I can parallel transport the vector back up to the equator. Do you agree? Up to the North Pole. And now this vector is pointing in a direction that is perpendicular to where it started off as. Do you agree? So I didn't tell you, how we're doing this parallel transport, what any of this means, but you can think of this picture with my finger. The vector started here. I translated it like this. Then I translated it along my path like this. Then I translated it back, and now the vector looks, it's pointing in a different direction than where it used to be. Okay? And so it turns out a lot of things in physics can be expressed as, you have some fiber bundle, and then you have some, whatever vectors on it, and whatever physical process you're studying is actually just the. Did I turn this on? Yeah, it is. It's green. It's green. Right? Okay. And whatever thing you're doing, whatever your physics is, can actually be expressed in terms of, oh, you're just like doing some parallel transport of some vectors. And the fact that this vector didn't end up in this, the same configuration as it was before shows that, okay, something interesting happens, where maybe you wouldn't expect it to. And that is, very vaguely why we might be interested in this. So do people remember, so here I have a fiber bundle. So I have, in this case, I have a vector bundle. So I have at every point, I have a vector space. Do people remember where in physics from a previous reading group we see vector spaces? Exactly. In quantum mechanics, right, you have a Hilbert space. Do you agree? And so the idea of what we will kind of end up with this whole topological insulator business is that you will kind of have your manifold of some parameters, maybe momentum or whatever it is. And at every point of that parameter, you're going to have some Hilbert space. Do you agree? And in that Hilbert space, you're going to have your states. And then, okay, depending on what the situation is, you will be interested in if I move around on my base manifold, so if I change around my parameters, how does my state change as I change those parameters? And that will be a very important question, okay? And so it turns out, on the sphere, okay, you have this idea that, okay, you go somewhere and then you come back and something new happens. On some manifolds, okay, that doesn't happen, okay? And so, but the idea is this whole scheme really lets you distinguish very qualitatively between kind of these cases where you have some non-trivial turning and twisting, or you don't. And that will become important later too. Yes?
Like a classically changing state, or
No, it's quantum mechanically. Though, I mean, these fiber bundles and all of this parallel transport does also appear in like classical mechanics, because I can reformulate a lot of things as like trying to find geodesics on some manifold. And okay, that is something I don't want to talk about because I need to actually prepare. I have not prepared. I'm just telling you fun facts. Okay, so this is what we would hope to do. The problem is, if we just started like doing it in this order of learning about parallel transport on vector bundles and then doing physics, we'll probably not really get to the physics. And so I don't want to do that. So now on to the structure of how we will structure our thing. We're going to meet mostly weekly. So this is not new for the people who have done reading groups before with me. We don't skip. Once again, though, if you can't make it for whatever reason, like, that's okay. And at the same time, I do not want to, make this very stressful for you. Like, at worst, you will need to come and sit in a room for about 1.5 hours and not understand anything. Like, you can probably do that. Okay. Mostly weekly. I will send out a let us meet every week on the Discord server and then book a room and schedule it. It will most likely be this room. It will most likely be Wednesday or Thursday or Friday evening. More likely it's going to be Thursday evening than anything. So that's how that is going to go. We will alternate weeks. Alternate weeks between physics and math. Physics and math. So we definitely have a lot more ground to cover in math maybe than in physics, because there's a lot more details. But there's definitely still quite a few things we need to learn in physics beyond just the postulates of quantum mechanics before we can understand what topological insulators are. And so, for example, this week we're talking about math. Next week, someone will need to present about physics. Okay, and then we will alternate. So how this will work? For every week, I will assign a reading, and I will need one volunteer for every week out of the existing people to present. So that there will be one person who will have to 100% do the full reading, and then come to the board like myself and explain it. whatever it is they read. Of course, everyone else is expected to do the reading as well, but okay, they will not necessarily need to be there and present every week. So yes, so assign a reading, and so every week there will be a assigned presenter. Sometimes I will maybe be able to get guest speakers to alleviate our efforts, and maybe it will be fun for you to meet other people in the math and physics department, other undergrads. So every week there will be an assigned presenter, and there will be a spreadsheet that I will post and pin. Yes, spreadsheet that I will post and pin in the announcement channel where I've been sending everything. And so the readings will all be there. And the sign up will also be there. Okay. So to help you with presenting, because this sounds scary, I will do my best to meet with the speaker a couple days before, so that if you're completely confused, we can clear something up, and so on and so forth. So meet. So I can meet with speaker. Week of. Okay, that's another thing. Also, do not be afraid that, oh, I need to prepare, I need to have a perfect presentation. If there's things you don't understand, that's the whole point of the reading group. There's things you don't understand. You come here, you say, oh, I don't understand this, and then we discuss, okay? As long as you've made some effort to try and do the reading and understand it, it's perfectly okay, right? And in principle, like, if people really can't do things over, like, it's exam season or midterms or whatever, we can probably either cancel, or I can just turn this into an office hour where you ask me questions in preparation for your Physics 356 midterm, and I help you with Physics 356 instead of learning this. But hopefully some of the things that we will see here will be helpful for you in your other courses. Okay, definitely will be for the second years. Okay. So yes, please do not be intimidated by any of this. This will be minimal work, as always. Okay. Yeah, no, but that was the summer is different. The summer is not the year. In the summer, I was free and not doing anything. Now I am busy, and if I am busy, then I will be like more mindful. Hopefully. Okay. Yes. Is there anything else that's really important? Yes, please fill out the Let Us Meet. We're back to Let Us Meet, because Let Us Meet started working for me again. Maybe I'll add Cabbage Meet once in a while, but okay. And then, yes, and as you remember, sometime in April, we will all have to present on this. Well, you will all have to present on this, but that's fine because that is in April, so we don't think about it now. But there will be pizza, I hope. Okay. To whom? Yes. So, good question. The directed reading program. There's a bunch of other directed reading programs that are happening with other supervisors. And so we will be split into rooms of like 2 or 3 reading programs per room. And then we'll just present to whoever's in our room. And it's like all of us have to come up with a 15-minute presentation, like for everyone. Okay, we'll see how many people show up next week and the week after. But, 15 minutes of talking amongst 4 people is like bird easy. Like you don't even have to know anything. It's fine. The difficult part is like answering questions, but because I'll say, oh, my group still has some second years, they'll be like very nice. They won't ask anything serious. Okay. Huh? Yeah. That's. There will be more. There's 2 more. What? No, there's 1 more third year, I think. But that's okay. Okay. And so yeah, but this you need to like talk to me about personally, so that we arrange times if you get assigned. So for this exact reason, I need a volunteer to present next week on the postulates of quantum mechanics, preferably someone from our previous reading group. So you will just have to kind of review basically what we talked about in the reading group in winter. Okay, good. So Trevor, or I was really thinking that Sylvia would do it, I feel like Sylvia is the person to talk about postulates of quantum mechanics. So it's either you or if you can convince Sylvia. So Trevor convinces Sylvia. Okay. This is what I would like to happen. This is what will happen. Okay. So
I'm just gonna like take a picture of this and then just send it. Right now.
yes, exactly.
Actually, can you like use like slightly? I need
Yeah.
tiny yellow.
So I you know I've already told her about this, and she's kind of said like, oh, maybe if I have time, probably not. But then now that there's more of you, then you can pressure her into presenting next week, and tell her it's going to be on Thursday at 6 p.m. I'll send out the let us meet for when it's going to be later today. But okay, you can guess when it's going to be. Good. I think I've talked about logistics for long enough. Yes. So hopefully, guys, please, if anything feels like we're going too fast or this is too much of a time commitment, just tell me and we'll do less. Right? Like, if you want me to spend less of my free time doing, volunteer work, I'm always happy to spend less of my free time doing volunteer work. Right. There will be suggested exercises once again, but these suggested exercises will be one suggested exercise a week at most. And yeah, like it will be like something from the reading. I'll be like, do this exercise in the reading, and that's it. Office hours. I don't know about office hours. I have my Math 240 office hours on Friday, but then there's like actual Math 240 students that show up sometimes, all the time actually. So maybe not, but you can like sit in the back and work on the problems together, because from what I remember in the past, when you guys worked on these problems, you didn't really ask me anything, you just worked on the problem and it was fine. So I will have a room booked Fridays, 5 to 6 p.m. for you guys to work on the one problem and ask each other for help and not me. Okay. You're not as good as me. Okay. Any more questions? I feel like I've talked about this for too long. So yeah. Office hours, MP 606, Fridays, 5 to 6. Tomorrow though they're 4 to 6. I have 2-hour long office hours. Oh, sorry, Friday, whichever day is Friday.
Right after their first quiz.
Whose first quiz? They have a quiz? Oh, I mean it's after their first quiz. I don't care. It's not before. Yeah, there'll be no one there. And plus, even then, like last 2 weeks, I had like 3 people on the first one and 2 people on the second one, which is infinitely more than my office hours last year when I held my office hours on Monday at 10 a.m. So, I call this an improvement. But though I will say that at the end of the year, when I started putting quantum mechanics problems, I had like 10 people in my office hours on Monday at 10 a.m. So that was very good. Okay, I want to stop talking about this. This is already like spent 30 minutes. Actually, this is kind of exactly where I want to be. This is perfect timing. I'm this good. Okay. So yeah, do people have a sense of what we might be talking about over the next year? Maybe. I sure don't. And yeah, the other thing is like, if previous reading groups were usually on material that I was very well familiar with, or at least a little familiar enough that I can like look at it and figure it out within 1.5 hours what's going on. Some of this connection on vector bundle things, I understand it. I understand intuitively what's going on, but I have no practice with any of the calculations. So I'm hoping that as you struggle with calculations, I will figure them out faster, and so that I learn that way. Okay. So the goal is for you to teach me. Okay. Now let's do a review of multivariable calculus. No. We've done this in the classical mechanics reading group like 5 times, and I explained it poorly the first time, but now I'll be better. Because now I've explained it to some high schoolers, and they seem to have understood, so surely. 5th time is the charm. Okay. Right. So, first of all, let's go back to the sphere and look at motivation for why we care. I said that one of the things that we're interested in is we're interested in studying these tangent planes to, say, a sphere or something else. Do you agree? So one way you can think of this is, right, I said I'm going to have some coordinate patches, right? Do you agree? And a coordinate patch is just a function from, so let's call this psi. This will just be a function from, okay, some open set in R2 to R3, right? And particularly this will be to my sphere as a subset of R3. Okay? Yes? So the idea is going to be what? So suppose this is my point P. And this is my point, okay, this point gets mapped to this point P. And if I want to figure out what the tangent vectors are here, right? What I maybe want to do is I want to say, okay, at this point, if I go a little bit this way, if I kind of look in this direction, what direction does that correspond to here? And if I look in this direction, what direction does looking in these coordinates, what direction does that correspond to on this here? Right? And what these kind of directions are, they're really these, this is the idea of kind of a best linear approximation. Right? I mean, that's exactly what the tangent plane to my sphere is. That's a best linear approximation of my sphere kind of at a certain point, right? And so this explains why we're going to want to begin by studying best linear approximations of some functions. Do you agree? And that's really like what calculus is. You study best linear approximations of functions. Okay, I will now erase this as, kind of motivation. And so let's recall some basic facts. Question 1, what is a linear function? What is a linear function? Please, someone enlighten me. Yes?
If you add it to another linear function, well, if it's a function of two arguments, it's like a function applied individually to all.
Okay.
Then same with the scalar multiplication.
Yes. So in other words, this respects the linear structure. Okay, you guys should have been first to say it. Well, the three of you. But okay. I failed as a TA. I've learned nothing. Granted, I don't think I really gave. Actually, were you in my tutorial? I don't even remember.
Yeah. Well,
Maybe.
it was
Okay.
in Howard's.
Yeah. At some point, I kind of started going to the one in McLennan.
I was in that one.
Oh, okay. Okay. Yes. Okay. So a function is linear if it does this. In other words, it respects the linear structure. Meaning what? Meaning if something used to be a sum of two things, it is a sum of two things. If something used to be multiplied by a number, it's still multiplied by the same number after. Okay? I will not go, I cannot keep talking about this over and over again, so I'll stop at that. So now we give a definition of a best linear approximation at a point. So, definition. Let f be a function from Rm into Rn. The Jacobian, sorry, the best linear approximation of f at point P, P in Rm, is a linear function, a linear function denoted DFP, such that f of x plus u is equal to, f of p plus u. Actually, let me write this in red, because this will be the most important equation that we will use forever and ever and ever, or at least for the rest of the class. Whoops, what am I saying? F of p plus u is equal to f of p plus df at p applied to u plus some r at p of u, with the condition where r has the condition r is of higher order, but really all that means is that the limit as magnitude of u goes to 0 of r at p of u norm divided by the norm of u is equal to 0. Okay, so in other words, this goes to 0 faster than a linear function. Okay. Right. So this is not composition, but like this is a linear function. I plug in a vector u into the linear function. So I plug u into this. Okay. Okay. I will now draw a picture that I've drawn hundreds of times before. Should I maybe go to the other board to draw these pictures? Yes, I will go there. Maybe, actually, I'll even push this over. Can you still see what I will be writing here? Okay, good. So now, why does this make sense? So let's draw a picture. Do I have some colors? I have some colors, good. So I have, okay. So I have my, say this is Rn, and say this is going to be my Rm. Do you agree? And I have some function f that goes between these two things. Yes?
Can you just leave it the other way around consistency with this board?
Oh, my bad. That's good. Okay, good. And say I have a point P. Do you agree? This function is going to map this to some f of P. Do you agree? So this is f of P. And this is P. All right. Now, I can ask myself the question. Suppose, so yes, as I move around here, right? I will kind of say I was to trace out a path here. Do you agree? Then f of that would be some path here. Do you agree? Okay. And so in Rn, I kind of have directions, right? And in Rm, I also have some kind of directions. Do you agree? Okay. So I can ask the following question. Okay, suppose I started at point P and went in this direction u, where u is some vector. Okay. So the question is, how would f of P change in that direction? Do you agree? Okay. And the question is, so if the question that we're asking here is, how not only not just how would it change, but how would it change to linear order. So if I start going in the direction u, where will the point f of p plus u kind of start moving as I increase u? Okay? Does that make sense as a question to ask? Okay. And so then this answer will be precisely df at p applied to u. Do you agree? So if I start changing p in the direction of u, in what direction and with what magnitude will f of p start changing to linear order, the first order? Do you agree? And so that is exactly what dfp composed with u is. Why? Because, well, I demand that the df is a linear approximation, it's a linear map. Therefore, it has to kind of map a vector at this point to some other vector at this point. Okay? All right. And so then you have this RP of u thing, which is of higher order, and we ignore it. Okay. So this dfp is also called, it's the best linear approximation, but it's also called the Jacobian. So this is also called the Jacobian. Okay. And so at every different point, I would have a different Jacobian, and it's just some linear map which kind of takes in directions in my base space and tells me after I map that going in this direction u, what direction is that going after I've mapped myself. Okay? This kind of makes sense? Okay. Let's look at a few examples. Okay. Let's look at a very simple example. Suppose I have the following map. The map is, so I have a map f from R into R2. The map does what? The map takes in t and sends cos t sine t. Do you agree? Okay. So do people know what the image will look like of this map? Circle. Exactly. So I have my map here. Okay, and then I have my unit circle here. Okay. So suppose I'm at a point P over here. Do you agree? And I say, okay, suppose I'm at a point P here, and I go a little bit in direction U to the right. Do you agree? I will have some corresponding point. I will have some corresponding point f of P here, right? And the question is, if I went U to the right, which direction will f of P shift? Yes. Do people see the question being asked? Okay. And the direction will be roughly given by the Jacobian, but I don't just want to look at the direction. I also want to look, if I take one step versus two steps, right? By how much does this function kind of stretch this unit vector as well? So I don't just care about the direction. I also care about how much it stretches. So, well, a linear map. Okay. So, okay. Can someone try and figure out what the Jacobian should be based on this? But, I mean, you've taken a course, so maybe. Hmm? Yeah, exactly. So they should give it a chance because this is complete the review. Yeah, exactly. Like this has to be completely familiar. Please, just tell me what the Jacobian is. I mean, something. Answer the question in whichever way you like. Yes. So there should be a negative sine t cosine t. Okay. Yes. So exactly. So I will be inputting in here u, and on the output I'll be getting some two-dimensional vector, which is the best linear approximation of this function in as I kind of move it in the direction u. Okay. So in that case, the answer is that it is this applied to, okay, multiplied by some number, whatever it is. Okay, do people see this example? Right, so this will be minus sine p cosine p times u. That will be my vector. All right, so now let's do this in general, Rn by Rn. Okay. Okay, I'll do it in the corner here, because I want that still to be visible. And okay, so my function f has n inputs or m inputs, right? And what does it do? It outputs some f1, x1, xm, all the way up to some fn, x1 up to xm. Do you agree? Okay. Yes? Suppose I go in kind of direction EI. What does this correspond to? So I'm going in the direction EI. What should that be? What should that correspond to? Which coordinates am I changing? Which coordinates am I not changing? So I have vectors. So I input numbers x1 up to xm, and suppose I started at some point, and instead of going in some arbitrary direction u, I specifically went in the direction EI from P. Which coordinate is that equivalent to changing? So I have x1, x2 up to xm. The xith coordinate. Do you agree? So, and all the other coordinates are what? They are fixed. Yes. So if I say I'm going in direction EI, that's I'm fixing all the coordinates except for the EIth one. I start changing stuff in that coordinate, right? And then I'm seeing how would the output change as I'm changing this xith coordinate. Do you agree? Yes. So in that case, the best linear approximation should just be taking the derivative of each of those functions with respect to xi while keeping all the other coordinates fixed. Do you agree? So this is, I think I talked about this in classical mechanics reading group, is the idea is if you don't know how to do a best linear approximation in every possible direction, but we definitely do know how to do a best linear approximation in one direction because we know what a one-dimensional derivative is, right? Then let's just fix a direction and do a best linear approximation that way as just a plain old derivative. Do you agree? So in that case, so the best linear approximation df at point P with respect to EI, this intuitively, like we expect, should be the vector df1 with respect to xi, df1 with respect to xi, sorry, dfm with respect to xi, all of it evaluated at P. Right? And so when I mean dxi, I mean keep all the other coordinates that are not I fixed, and then take a derivative with respect to xi. Do you agree? Yes? But I just told you how df of P acts on EI. So how it acts on every single direction. So from this, I should be able to directly reconstruct what this matrix has to be. Yes? Do you agree? So let's write down what this matrix has to be. And, I will not prove that this is indeed the best linear approximation. So how would you do this? So once I write down this matrix, then all that is left for you to show is for you to show that I can express my function as this, as this, plus that matrix applied to something, plus some other part, and then you're going to spend a lot of time having fun showing that this part goes to 0, right? That's what you're going to do in 257. You're going to spend weeks on it, and I don't care. Like, just, okay. So can someone tell me what this matrix has to be? So if this is EI. So if this is, if I apply this matrix to EI and get this, this is the what of the matrix. This is the ith column. Do you agree? So then this matrix has to be partial f partial. So this is the first column. So x1. So this is 1 partial f. Oh, sorry. This should be n. Whoops. N partial x1 partial f partial f1 fn, correct? Yes, fn partial xm. And so in general, the ith row jth column is partial f ith row partial x jth column. Do you agree? So why is it so? The inputs are the directions that I'm going in here, right? So if I'm going in the jth direction here, that means I'm varying the jth variable. So the derivative has to be with respect to the columns. Do you agree? And then because I'm looking at so on the output here, right, the ith row tells me how much am I going in the ith direction over here, right? So that means the function that I'm differentiating out of these has to be the rows. Yes, all of this is evaluated at B, correct. And so this is here as per the notation I defined. Yes, so all of these are evaluated at B. Okay. And I think the claim is that if my function is nice enough such that all of these partial derivatives exist, so right, all of these one-dimensional derivatives exist, then this is indeed a best linear approximation with these properties. So the theorem that we will not prove, and I will literally write it in the margins. Theorem, if all dfi dxj exist, then that implies that what? What am I saying? Right. Then that implies that d f of p defined as matrix above is indeed a best linear approximation, a best linear approximation in the sense of the definition.
Just to clarify, this is a best linear approximation and not necessarily like an actual. It doesn't imply the existence of an actual derivative.
So what I just said is that it implies, so this Jacobian thing is the derivative in multiple dimensions.
Okay, yeah, because like we did a thing today that was weird.
So I'm saying that if the Jacobian exists, then all of the partial derivatives exist, and if all the partial derivatives exist, then the Jacobian has to exist. Oh, is it? Well, if I can differentiate in every entry, I think I can.
No, we didn't.
What was the suggestion? Oh yeah, sorry. Exist. Yeah, you're right. Sure. So if all of I exist and are, say, C1. Okay, sure. Exist and they are C1. Okay. Same difference. Well, not same difference. I agree, but sure. Essentially, if all of these exist and are sufficiently differentiable, then this will have this property. And you can also show that if there exists a best linear approximation, then there can be only one best linear approximation, right? Okay, so you can only have one derivative. That makes sense. Yeah, you're right. They do need to be continuous, because otherwise you have like these weird cusps and it doesn't work out. Yeah, it's a good point. But do people see in what sense the Jacobian is a derivative just in more dimensions? Yes? Or, well, do you see in what sense a derivative in one dimension is just a Jacobian in one dimension? Maybe that's a better way to say it. Okay. Now we should probably say two things. We should say the chain rule, and we should say the change of variables theorem for integration. Okay. Chain rule is on your homework. Change of variables is like halfway through the course. Okay, and then someone is going to be presenting on, so the math topics, the next math topic is probably going to be like manifolds or something, and the next one's going to be differential forms again. But we presented on differential forms so many times that surely someone knows something about differential forms. The thing is, like, the more I think about differential forms, the more I realize, like, I don't quite know a compact way to talk about them yet. That doesn't require hours of discussion. Okay. So let's show change of variable theorem. Let's draw a picture. Okay. So I have my function g going from, I don't know, Rm into Rk. I have my function f, f going from Rk into Rn. Okay? And so suppose I have a point here, which gets mapped to a point here, which gets mapped to a point here. This is P. No, I wanted to use green, right? This is P. This is G of P. This is F of G of P. Do you agree? And so what's the point? The point is, okay, suppose I have some direction here, U, right? Do you agree? If I have some direction here, U, then by G, it's going to be sent to some direction. What direction? By G, this direction U gets, this vector U will get sent to a vector here. What vector? What's the vector going to be? Tell me just the letters. Yes, exactly. Guys, stop thinking, searching for meaning in math. It's just say the letters in the right order, and then I'll be happy. I can't tell the difference if people actually understand something or they just can say the letters. Those two things seem to be like physically equivalent. So I guess it doesn't matter if you actually understand anything. Okay, but now look at what I have. I have dgp of u, which is a direction, and I want to best linearly approximate that as using f, right? So now this is some new vector, and I can push it forward with the Jacobian of f. So let's call this vector, I don't know, v. So this vector v by f will get sent to where? To, just say the letters. df at g of p, correct? A v applied to v, which is just dg at p applied to u. Do you agree? So in this case, what you can read off the change of variables. So the chain rule theorem. The chain rule is what? So the best linear approximation of f of g at point P is what? Exactly, that. I don't know if you've seen the video where there's a professor and then he's giving exam to these an exam to these students, and he's asking them how does something look like, and then they keep trying to give an answer, and then he's like, okay, do you know what I'm talking about? Yeah, exactly. So that's a very good answer. It's a very instructional video. I found it to be very useful. Okay. I'll send the announcements, but it has too much swearing in it, maybe for me to. Okay. G at P composed with D with G at P, right? So the point of the chain rule is essentially if I take this and move it here, and then take this and then apply it here once again, and then sorry, what am I saying? Yeah, the point of the point is that the best linear approximation of the composition is the composition of the best linear approximations of the pieces. Yes? And this is something that you can once again spend a lot of time proving, and let's prove it in like 5 seconds. Okay? So what do I have? So I want to compute f of g of p plus u. Do you agree? Yes. According to this definition, it is what? Well, let's expand GP of u first. F of g of p plus u is what? It's g of p plus dg at p of u plus some r at p of u. Do you agree? Yes? Now, I can group this in the following way. I can group this. This would be kind of a v. Okay? And I can expand this again using the same formula for f. Right? Okay. So I'm implicitly, sorry, for this chain rule, I'm implicitly saying that G has to be differentiable at P and F has to be differentiable at G of P. Okay, but you're in second year, you should be able to infer all of these assumptions that I'm making. Okay, so now let's expand this according to that same formula, right? Because that's all we know how to do. All I know how to do is plug symbols into other symbols until I get the right combination of symbols, and then you just do pattern recognition. Okay, I have F of G of P plus df at G of P applied to dg of P u plus df at G of P applied to RP of u. This is a linear term, and then plus. So I'll kind of do it R1, R2. So this is kind of R. This is the one for the one for G. This is going to be the one for F at G of P. And I plug in RG at P U. Do you agree? Yes? I just plugged in that formula twice. That's all I did. So it's like we're assuming, suppose that formula holds for both of these functions at the appropriate points, plug things into the formula. Yes? And now, what can I notice? Okay, first of all, this is linear. This is the linear constant, right? So this very much looks like a very good candidate for df of g. Right? This very much looks like what we want. Do you agree? This is the constant term that I always want. So this is the constant term as expected. Do you agree? So that's good. So it's kind of, this looks like this piece, right? This yellow piece looks like this yellow piece, and then the rest looks like the rest. Do you agree? So essentially, if you wanted to fully rigorously prove that this composition is indeed your derivative, then you want to show that this, if you plug in u into it, and then divide by the norm of u, then that goes to 0 as u goes to 0. Do you agree? However, this should be more or less clear. Why? Because, so, okay, this is a linear function, so that goes to 0 as u goes to 0, right? But then this thing is of quadratic order, so this has this property, right? And surely if I plug in something quadratic into something linear, then it would still be at least quadratic, right? And then here I'm plugging into something that's of higher order into something else that's of also higher order. Then surely that will also be of higher order. Like, this is just like you have to sit around and do a little bit of delta epsilon for like a couple hours. Or actually, maybe for this you need to define the norm of a function. But okay, these are all not very enlightening details. Well, they're somewhat instructive, but not too much, right? Do people see why this would be of higher order? Yes? No? Yes? Do people see why, on the basis of this being of higher order and this being a constant term, and of the fact that the best linear approximation should be unique, I can conclude that this has to be my best linear approximation for F composed with G? Okay. Proof completed, QD. Like, yes. And the other thing is actually, like, this is the definition of the derivative that Arnold uses. And I feel like it's much easier to prove things with this, because I feel like it's very easy to kind of prove that like some of these things go to 0 because they're just compositions, versus what you do in like Moncrief's is like long and complicated, and I have to look at it each time. Like, some of those limits I just don't remember exactly how they work, and I have to like really read through it because they like divide stuff, and, right? Yeah, well, in Spivak as well, like in Spivak you still do like a limit of something over delta t, and then you have to like actually do stuff. Versus here, I just have to like prove that some compositions of functions that go to 0, and that's like I think I can do this if given enough time. But then like whatever Spivak does, I like don't remember. It's complicated. Okay, let's do the last thing. Let's do change of variables in 10 minutes. Okay, so chain rule is clear. What people understand this picture? Yes. Okay, suppose I have a set V, which is a subset of Rm. Do you agree? And I want to find the volume of this subset. Okay. So the volume is going to be what? It's going to be the integral over V. So actually, let's not use V because then that's confusing. Or maybe, yeah, that's fine. So the volume of V is just some integral over V. Do you agree? Of the function 1. So I have a, yes. Yes. Do you agree? So the volume of the subset is just the integral, whatever that means, of the function 1, right? So it's 1 on the set and 0 outside of the set. Or I mean, it doesn't matter, just 1 on the set. And I can integrate that, hopefully. Not always, but in every reasonable physical case, we'll just integrate it. Okay. Now suppose I have some subset, some other set U, and I have f from u to v a diffeomorphism. Do you agree? Diffeomorphism means the derivative exists at every point and it's invertible. Right? So dfp exists for all p in u, and this is invertible. And invertible. Right? So in some sense, u has to be like it's the same as v under this transformation f. Do you agree? U, I mean, also in Rm. It has to be in Rm because otherwise, like you can't have Rn cannot be isomorphic to Rm. That is a loaded statement. Proving that requires quite a bit of effort, but I don't remember those details that well. They're actually quite interesting. But, okay. Oh. Okay. We're almost done. Right. Actually, one thing about being invertible, that kind of means that the Jacobian has to be invertible at every point. But okay, I should have mentioned that earlier. Too late. If I didn't say it, then it doesn't matter. Maybe that's false. Maybe don't think that way. Okay. So let's draw a picture. And this is actually in the newest edition of Axler. So in the newest edition of Axler, the change of variables theorem is discussed. Because this is a linear algebra statement, really. Well, it's a statement about determinants. So I have my set U. Actually, let's draw it like this. I have my set U, which is ideally something we understand very well and is something that's very nice. And then I have my set V, which is maybe somehow complicated. Right? And so the hope is that it's very easy to figure out to integrate something over U, but maybe very hard to integrate something directly over V. Do you agree? Okay. So what can I do? I can kind of tile this by like little squares, let's say, or cubes or whatever it is. Tile with whatever you want. Do you agree? And so then, little cubes. And so then, once I map it by f, right, this would be mapped to some stretched cubes, maybe. Do you agree? Yes? Yeah, they might, well, these stretches might not be linear. But the argument is that if we take small enough cubes, then the stretches will be linear. Do you agree? So these are non-linear stretches. But then if I make very small changes, let's look at one particular cube at a specific point P. So I have a point P, and I have kind of a little parallelogram with these two directions, right? And it's going to be stretched in some way. In what way? Maybe like this, where so okay, say this is E1, this is E2. This is going to be stretched into df PE1, and this is going to be stretched df PE2. Do you agree? Yes? No? Maybe? Do you agree with this? Okay. So this means that, suppose my side lengths here, well, I chose E1 and E2. Let's say that these are side lengths, I don't know, epsilon 1 and epsilon 2. So this is epsilon 1 E1 and this is epsilon 2 E2. These are the side lengths of my cube, of my square. Do you agree? So square with epsilon 1 E1 and then epsilon 2 E2. Do you agree? And so then this gets mapped to some parallelogram with sides epsilon 1 df at PE1 and then epsilon 2 df at PE2. Do you agree? Now all I need to do is compute the volume of this and add up over all of this. Compute the volume of this and add up over all the squares. Do you agree? So suppose I have two vectors. Do people remember what the area of the parallelogram that those two vectors make is given by? Yes. So I just look at the determinant of the matrix. So the area is the determinant of the matrix where these guys are the columns. Agree? So this is df. So the first column is df. Well, I mean, yeah, this is literally just the determinant of df at p. Do you agree? Times epsilon 1, epsilon 2. Do you agree? But, well, actually, no, false. This is dfp, then one column is multiplied by epsilon 1, the other one is multiplied by epsilon 2. So then I can factor it out like this. Do you agree? Okay. So in principle, if this wasn't a two-dimensional drawing, was an n-dimensional drawing, I'd have parameters epsilon 1 all the way up to epsilon n, right? And I would be summing over all of the squares, right? And epsilon 1, epsilon n would be the width of my squares, right? So it would be, I'd be summing over points x1 up to xn, right? So, and say this is like of length from 0 to L degree. So I am summing up over how many things? I'm summing up over, so from over P equals to, you know, P equals whatever, P equals 0 everywhere, to P equals to L over epsilon 1. Do you agree? Okay, so I'm just kind of adding up over all of the squares. I have a square at every single point, and then I add up over all of these squares, and I have this. Okay, and these squares are of some width. Do you agree? But okay, if I want to turn this into an integral, I send epsilon to be very, very small, all the epsilons to be very, very small, and I just get that this is the integral now over u of what? Of, well, this just becomes the dxi's, right? So this is an integral of dx1 up to, let's put this upstairs, dx1 up to dxn of the determinant of df at p. Okay? So this is all it is. I have some little square. The determinant of my Jacobian tells me how much it gets stretched by, and then I just integrate that to add up over all the squares. This is all that the change variable theorem is, and you will go over, you know, great lengths of proving it. Okay. So let's write this down as a proper. I just gave you the proof. I didn't give you the theorem. Let's write down the theorem. The theorem is that the integral of the volume 1 is equal to the integral. Sorry, the integral over f of u, the set f of u, is equal to the integral over u of the determinant of the Jacobian of f if f is a diffeomorphism. Okay? And let me write down one more theorem, and then we'll stop. I'll really write down the exact same words. So another statement that I will write down is if I have some function g of x that I'm integrating over v, over f of u, over the set f of u, And this will be the integral of g of f of p times the determinant. Actually, the absolute value of the determinant. So this should all be absolute value. Sorry. Take the absolute value of the determinant. Right, because I could have negative areas if I mess up the orientation, but I want to only be looking at positive areas. Pardon? Yeah, so here, yeah, absolute value, thank you. Determinant of, okay. Like, once again, I feel like if you understand this geometric picture of what's happening with this proof, then actually proving it should be doable in like, actually no, it would be very difficult. It would still be very difficult. Because you need to prove like these like inverse function theorems and whatnot and care about all of that, and the inverse function theorem requires some time and it requires effort. But geometrically the ideas behind it are very easy. And usually even for mathematical purposes, you only need to understand the geometrical idea, and the proof itself of how you do the inequalities is like not that significant. Like, I think most people in the math department, if you ask them, prove the inverse function theorem for me right now on the spot, it would take them like a couple hours. Inside of the video, I shouldn't say that publicly, but it took our professor like a while. And like fully understandably, I read one piece every time, and every time I read it, I'm confused. Because it's just like, oh, let's like relabel this complicated thing into this other letter, and then like show that that goes to somewhere. Okay, it's too much. Well, it's not too much. It's important. People should do this, but you shouldn't forget that this is actually what's happening in all of those details. Okay, so next week somebody will present on the postulates of quantum mechanics. So hopefully that will be a little bit new for you and good review for other people. Yes. Okay. In that case, we're done. I'll post the recording.